Let's look at a special case of equimolar counter diffusion. So let's look at two bulbs there, which are joined as indicated in equimolar counter diffusion fig 1.31. So this shows two gases A and B at constant total pressure in two large chambers connected by a tube where molecular diffusion is occurring at steady state. So it's not true. Understand that PA1 is greater than PA2. So in this case, saying PA1, this one here, this is greater than PA2. Then PB2, this one, is greater than PB1. So you understanding that movement is from a region of higher concentration to a region of lower concentration, you can assume which direction A is going to move and which direction B is going to move. And that's indicated there is the flux JA and the flux JB. And the driving force is the difference in these partial pressures, which would obviously be a difference due to difference in concentration. So the total pressure is constant throughout. So net moles of A diffusing to right must equal the net moles of B to the left. So JAZ is equals to JBZ. Then fixed law for JB is indicated there. Then as you can see, PT equals to PA plus PB, which are partial pressures. Then total concentration there is concentration of A plus concentration of B. So if we differentiate both sides on 1.34, it becomes GCA minus GCB. If you differentiate a constant, it becomes 0. Then equation 127 to 133, there we have JA is equals to minus JB as indicated by equation 316. So this minus and the minus for the JB, so this becomes a positive. This gives us a positive. So if we continue our manipulation with these equations there, now our substituting equation 135 there, 135. So this, we are then saying this is substituted for 4 by this or vice versa. Then we are left with our DAB is equals to DBA. meaning this shows that for a binary gas mixture of A and B, the diffusivity coefficient DAB for A diffusing into B is the same as dBA diffusing into A. So let's look at an example here where we have got our ammonia gas is diffusing through a uniform tube, 0.10 meter long, containing nitrogen gas is our B there, and pressure 1.0132 times 10 to the power 5 pascals and 298 kelvins. Right, so the diagram is similar to the fig 1.31 at point 1 there. Let's just go to fig 1.31 being referred to there. And this is the fig 1.31, which is being said to be similar there. So we can rush back where we were. Right. So this question is saying calculate the flux of ammonia Ja at steady state. And we then repeat for Jb, which is for the nitrogen. So our solution, if we have our diagram there, then our data indicated is our gas constant, temperature, total pressure, PaV1, PA2, PJB. All this information has been extracted from the question there. Then let's go to the solution. Sorry, I already have that there. Something didn't okay correct there. Right. So calculate the flux JAB. So we want to see how we get to this point. So the data is given in terms of partial pressure. So we'll make use of the partial pressure form of our equation. And you can see that all the values are indicated there. And simply substituting for that into this equation, we get our solution there is indicated, and as I'm underlying then. So the same applies then again to our JB. We're using the equation. Instead of PA1, we are now making use of PB1. And then we make use of the equation PT is equals to PA1 plus PB, so that we determine the value of PB here is indicated there. Then likewise, our PB2 is also obtained making use of the same equation as indicated on your screen there. Then we now all have all the data. Then all what is left is for us to substitute that into the equation. And please let's make sure that our units are consistent throughout there. All right. So thank you.